Hey, what's up, calculus class? So unfortunately, we have to proceed with the notes for Chapter 8 for this online learning day. I really think that this is a pretty straightforward lesson, and I don't think there's anything too difficult about it. So I think it's actually working out pretty well that this is going to be done online. And again, I really hope that you guys do this before the upcoming Friday, where we can move on to Chapter 2. It'd really help with the calendar that we have for us. Um, if we keep getting online days, um, we'll discuss what that might look like, but we'll just try and take it one day at a time. But in Chapter 8.1, really what we're talking about here is we're talking about the um, the relationship between accumulation and net change, area under a curve. So, um, before we get into that, let's review what we know about velocity and position. Um, we know that the derivative of a position function is velocity, right? So if I have some sort of a curve like this and it represents position, well, the slope at a point is the pretty much the velocity, right, at that certain point. Now, if we say that, for example, we have a function that is represented as v of t, so maybe this is the derivative of a position function v of t, well then the area underneath the curve represents the positioning. So how much position, right? Um, if I have a velocity function, so let's say I have a coordinate plane and some sort of function, and this is v of t. Okay, well, what we know about v of t is that if v of t is positive, so this is the positive side, this is the negative side, if the velocity is positive, what that means is that the positioning is moving forward. It's moving in a positive direction. If the velocity is negative, like down here, what that tells us about the positioning is that you are moving in a negative direction. Okay? And if the velocity is 0, so at this point right here, maybe at this point right here, then your position is stopped. Okay, so if there's like some sort of line that you're walking on, if you label one side as forward negative or something like that, if you walk forward right here, then we would call that positive velocity. If you're moving backwards, it's negative velocity, and maybe the times that you turn around, that's whenever your position is stopped, something like that. Okay, so make sure we understand that. If velocity is negative, you're moving in a negative direction. If velocity is positive, you're moving in a positive direction. If velocity is 0, you're stopped. Okay, now let's talk about what displacement is. So displacement is the distance an object has moved from its original starting point, from its initial starting point. So if it starts at 5 meters or something like that, or moves is 5 feet ahead, and then what we do is if we calculate the area under the curve, then we can find its displacement. So pretty much it's the net area between the curve, and that should be the x-axis right there, not curve and curve. Okay, so here for net area, what that means is that it accounts for the negative area here. So this might be how much you walked forward, this is how much you walked back, and this is how much you walked forward. Now you could have walked 10 feet forward, 5 feet back, 3 feet forward, but essentially what that means is that you have to treat it like 10, -3, +4, something like that. And so your displacement would have to be 10 plus 4 minus 3. Okay, so you have to use negative area when we're talking about displacement. Okay, so it's how far you've moved away from your initial starting point. Okay, how you can find displacement is by integrating velocity that's how you can find it. That gives you the displacement, because whenever you integrate a function, it will account for both positive and negative. Okay. But now there's something called where we talk about total distance traveled, which it doesn't care if you're moving forwards or backwards. It doesn't care about that. It just wants to know how far you've gone total distance. So what this means is that whenever we take the integral, we have to use the absolute area that is under the absolute value of the area under that is beneath the x-axis. Okay, so absolute value is what we're going to need to find total distance traveled. Okay, so here the total distance traveled would be 10 plus 3 plus 4, because it doesn't matter that we moved backwards here. It's not talking about displacement. It just wants to know how far you actually moved total, how many units you moved. So that's the difference between displacement and total distance traveled. So in these examples right here, I pulled this one from your book. You have a couple of these for your homework assignment. But let's walk through this one that I did here. This is number 2 here. So in exercises 1 through 8, the function v of t, right here, in meters per second of a particle moving along the x-axis. Use analytic methods to do each of the following. Determine when the particle is moving to the right, to the left, and stopped. So first of all, I went ahead and drew this function right here, 6 sine of 3t. So 6 is its amplitude, how far it goes up and down from the axis. 3t, now because it's 3, that shortens its full length of the period. So instead of going from here back to its starting point in 2 pi, it's going back in 2 pi divided by 3. Okay, so in any case right here, we only want to know from 0 to pi half. So here's pi half right here. So we come along here, this is its velocity up until pi halves. Okay, now I note here that it crosses the x-axis at pi thirds. So that helps me distinguish when I'm changing, when the velocity goes from being positive to being negative. So when does it move to the right? It moves to the right when the velocity is greater than 0 or positive. So here it has to be from 0 to pi thirds. That's whenever it is positive. So not including 0 and not including pi thirds. Okay, because that's whenever it's equal to 0. That's when it's going to be stopped. And it's moving left when the velocity is negative, less than 0. So from pi thirds has to be less than t, has to be less than negative pi halves. So equal to negative pi halves because we're still negative down here. And again, when will it be stopped? Well, at the beginning, t equals 0, and at pi thirds when it essentially maybe goes from moving right to left. Okay. So B, find the particle's displacement for the given time interval. If s of 0 is equal to 3, what is the particle's final position? Okay, so the particle's displacement, how much did it move? Okay, so we have to account for negative area. Displacement means you have to use negative area. So, and also right here, initial position. Okay, so its initial position right here saying it's starting 3 units at unit 3 or something like that. That's where its initial position is, and then from there 3 units. It might be moving left and right, certain amount of distance, but that's where it starts here. Okay, so here it's starting at 3 units wherever it might be. It's moving forward here, or I guess you could say to the right, and then moving to the left here. Now to find the total displacement, I just need to find the integral of this curve from 0 to pi halves. So I have the integral of v to t dt from 0 to pi halves. Find its antiderivative, calculate all of that, and to make it short, that it comes out to be 2. So the total displacement from here to here is 2. Okay, so that's how much it moved right and left, accounting for both of those. but considering that we started at 3 units, okay, we ended up with 2. Okay, so basically we started at 3 right here. It looks like we moved to the right, then we moved to the left a little bit, and we ended up right here at 5. So our displacement was 2 units total, and we ended up at 5. For C, to find the total distance traveled right here. Now total distance traveled doesn't really, right here, find the total distance traveled. It doesn't need its initial position. It's irrelevant. We just want to know how far did it move from its initial position, how many units did it move forward and backwards. So we're going to need absolute value. So we have 6 integral of pi thirds, integral from 0 to pi thirds, so that's from here to here. So if I find the area under the curve from here to here, that will tell me how much it moved to the right. This right here will tell me how much it moved to the left, but I want the absolute value because I don't care that it's negative. In any case, if you find those, we end up with it moved a total of 6 units. Okay? Alright, so you should have some problems like that. Hopefully that's a good outline of what this is. I know it's pretty quick, but shouldn't be too difficult. Okay. Now here, so well, let's make sure, if I go over to the homework right here, I just want to make sure that you guys have a good idea of what's going to be in the homework. So you're going to do these examples right here, 1 through 6, okay? I think you also have right here 12 through 16. So in this example, you're using the same concept. So what is the particle's displacement between t equals 0 and t equals c right there? And you can notice that yeah, in the problem above, it does give you an initial position right there, but okay. So keep that in mind. The area under the curves are given right there, so you should have those, okay. Notice that 15 and 16, they're the same question, but different interval, so keep that in mind. 17 through 20, again, you're going to be using the same concept, so find where the particle is at the end of the trip, find the total distance traveled by the particle. So for 17 through 20, you're going to be using these graphs and answering those 2 questions right there. But again, all using the same concepts of what we just talked about. Okay, and then you have 21 through 27. So these are a bunch of story problems right here, and the story problems really aren't too bad. But let's look at this story problem right here. Potato consumption. So from 1970 to 1980, the rate of potato consumption in a particular country was C of t equal to 2.2 plus 1.1 raised to the t power. Millions of bushels per year, with t being years since the beginning of 1970. How many bushels were consumed from the beginning of 1972 to the end of 1973? So I'm going to set up this integral using years 2 to 4, because 1972 pretty much to the end of 1973, so that's from year 2 to year 4 right there. So basically, the key word here, the rate, see right here from 1970 to 1980, is that this is a rate function right here. So it's telling you how much is changing. So the rate at which millions of bushels per year are the consumption of them. So rate gives it away that this is a pretty much it's a slope form. It's a slope function. And which means that if I integrate, I'm finding how much, how many bushels, okay? Not a rate, but how much, okay? So basically, I'm just going to take the integral from 2 to 4 of this function. You can use a calculator, and you can come up with this number right here, which gives you 7.066 million bushels, okay? Some of these right here, you don't, if you can solve the integral without using a calculator, please do so. Some of them you might need to use the integral calculator, but in any case, so like 21, I think you can integrate this function pretty okay. But 21, 22, 23, 24 are all very similar in that you're given a rate function. So you have a story problem. You're given a function that represents the rate of how something is changing, and you need to integrate it, find the area under the curve, which tells you how much. Okay, so there's those right there. Okay, and now let's try this problem here, coming and going. So many problems involve pretty much what this is saying here is that these problems that we're going to be working on also, not only do we have problems where the rates are affected with something that might be going into something, but something that might be going out of something. So in this example here, we're talking about an amusement park, and we're given the rates at which people are entering into the amusement park and the rates as people are leaving the amusement park. And so at the end of a certain time period, how much are there total? So from noon to 6 p.m., the rate at which people enter the amusement park at time t is given by e of t, for which the graph is shown in figure 8.3. So in this figure on the left right here, this function shows us how many people are entering into the amusement park. Okay, t equals 0 is noon, and t equals 6 is 6 o'clock p.m. People are also leaving at a rate of L of t, and that function is given to us as an equation rather than as a graph. So this right here is a function that represents how much are leaving. If 3,000 people are in the park at noon, so keep that in mind, initially there are 3,000 people. How many people are in the park at 6 p.m.? Okay, we have to consider the fact that people are entering and people are leaving. And then we'll talk about this right here. But first of all, let's find how many people entered the park from 0 to 6, and for that we're going to use the area under the curve. So you can see how I did that here. Notice that one of these rectangles represents 100 people. So I calculate the area under for the full size boxes that we have, and I get 2,800 right here. And then the area for these sections right here, just find the area using triangles. So I get 300 here, 100 here, for a total of 3,200 people that entered into the park from noon to 6 o'clock. Okay, now if we keep in mind that there were already 2,000 people at noon, then that means if no one was leaving, we would have 6,200 people in the amusement park at 6 o'clock. But now we have to consider that there are people that left, and for that we're given a function. So 50, I'm taking out the constant, times by 0 to 6 of this right here. This one, again, I would just use a integral calculator. You can integrate this part right here. You'd probably have to use integration by parts. Totally possible. I used a calculator, but I got 2,106 people left from noon to 6 o'clock. Now, if we take the total people that were there and entered into the park, we subtract 2,106 from that number, then at 6 o'clock there were 4,094 people in the amusement park at 6 o'clock right there. Okay, so you're going to have a problem very similar to that right here on 25. So getting onto a ride is talking about people who jump in a line and jump out of a line, or go or basically essentially already go through the line, who jump onto the ride. But yeah, it's a very similar problem, so keep that in mind. Okay. Let's see, is that pretty... Oh, well, one other thing I wanted to note, 26. So keep in mind 26 is probably as difficult as your problems are going to be. So in 26 it says, at 6 a.m. a tank holds 2,500 gallons of water. Over the next 18 hours, it is being filled at a constant rate of 100 gallons per hour, while water is taken out at a given rate by that function right there, gallons per hour, where t is measured in hours after 6 a.m. how much is in the tank at midnight when t is equal to 18. So for this one right here, it's very similar, okay, to what we just did. You have to keep in mind that there's already water in the tank. Water is entering into a tank, okay, so how much entered into the tank over 18 hours, given that it was being filled at a constant rate of 100 gallons per hour. And then, once you have that, you have to subtract how much came into, or how much left the tank, modeled by that function right there. So if you take the integral of that given function from over the given interval, then you'll find how much left, and you just have to accumulate all of that together. Okay. And then for 27 right here, that's going to be this example right here. Should be very similar, but it's asking you to essentially use the trapezoidal rule. So you just need a refresher for this one right here. But a pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour, as shown in this table right here. So 5 minutes, up to an hour. How many gallons were pumped during that hour? So we're going to use the trapezoidal rule. Just as a refresher, a trapezoidal rule is where you take h divided by 2. H is the given interval, b minus a, so in this case 60 minus 0, given interval, divided by n, and n is 12, how many intervals there were. Okay, so that's 12 intervals. So h is 5 divided by 2, and I'm taking the first right here, first value, plus 2 times the second, plus 2 times every one of these values up until the second to last, plus 63. So this right here is your reminder for how the trapezoidal rule is used. And if you do that, you should get that many gallons right there. And you will find that example 27 is very similar to that problem, okay? Just using the trapezoidal rule, okay? And remember that my solutions are available in Canvas, okay? So I hope that this was helpful. Okay, again, I apologize for having to do this lesson online through video. I hope it's not too difficult. If it is, please come prepared on Friday with any questions that you have. And yeah, but hopefully it all works out pretty well, and I hope you guys enjoy the rest of your time out of school.